In this video, we will continue our look at equilibrium and aqueous solution problems. We're going to start with some titration problems. So we're still working out of chapter 17, and we're in section 17.3, which is on acid-base titrations, and we look at a few different types of titrations. The first one that we're going to look at here in exercise 17.7 is when we have a strong acid, strong base titration. So we're asked, what is the pH when 49.0 milliliters and then 51.0 milliliters of a 1.1 molar sodium hydroxide solution have been added to 50 milliliters of a 0.100 molar hydrochloric acid solution? Sodium hydroxide and hydrochloric acid are both strong. Sodium hydroxide, strong base. It's going to completely dissociate into sodium and hydroxide ions. The hydrochloric acid is a strong acid, which will completely dissociate into hydrogen and chloride ions. So we're looking at two different points in the titration. One at the addition of 49 milliliters, and then the other at the addition of 51 milliliters. So the first one at 49 milliliters is just before the equivalence point. So the pH is going to be determined by the amount of acid that has yet to be neutralized. The second one here, the 51 milliliters, is just after the equivalence point. So the pH is going to be determined by the amount of excess base. We can observe this here by looking at the titration curve on page 738 in your textbook, and it's also in your notes. This titration curve here is of the strong acid and strong base, and it happens to be hydrochloric acid and sodium hydroxide. And we can see on this titration curve that 50 milliliters, if we kind of follow that up, 50 milliliters is the equivalence point. So we're going to be just a little before that and a little bit after that. So the first thing that we're going to do when we look at our calculations here is we have 50 milliliters of solution, which is 0.05 liters, and we have 0.1 mole hydrochloric acid, which means when it dissociates, will produce 0.1 moles of the hydrogen ions. So the molar concentration of that would be 0.10. So we set up our calculation here, and we end up with 5.00 times 10 to the negative 3 moles of the hydrogen ion. So this is just the number of moles in the of hydrogen ions in the original hydrochloric acid. So we multiply the volume of the solution and the molarity. That gives us our number of moles. And we can do the same thing for the number of hydroxide ions, or the number of moles of hydroxide ions in the 49 milliliters of the NaOH solution. So we have 4.90 times 10 to the negative 3 moles of hydroxide ions. We are not at the equivalence point yet, so there are more moles of hydrogen ions present than the hydroxide ions. So hydroxide is going to be our limiting reactant, so we have to do a little bit of a calculation here. And like we did in the problem we worked with the buffers, we have sort of an ice table here, but it's more of a stoichiometry table where we're really looking at before the reaction. So initial would be, before the reaction. And then we have a change, and this is going to help us find our limiting reactant. And then we'll have equilibrium, which we consider to be after the reaction. When we look at what's actually happening here in the reaction, the hydrogen ions and hydroxide ions will combine to form water. So because we're not quite at the equivalence point yet, like I mentioned, we're going to fill in. Hydroxide is going to be our limiting reactant. So 5.00 times 10 to the negative 3 is our hydrogen ion concentration. We calculated that. Our hydroxide concentration, we calculated that, 4.90 times 10 to the negative 3. Again, they're not even because we're not at equivalence point. We're still on the acidic side of the equivalence point. And water being a liquid, we don't consider water at all. We don't have to worry about what's going on there. Since we have less hydroxide and it becomes our limiting reactant, we're going to run out of it. So it's just going to be minus 4.9 times 10 to the negative 3. And we're going to do this to the hydrogen ions as well. So that we have 0.10 times 10 to the negative 3. And so that's how much we're going to have of our hydrogen ions after this reaction has occurred. Now, because we're adding the sodium hydroxide to the initial 50 milliliters of solution, we have to account for that. So we have 99 milliliters now of solution, which is 0.0990 liters. So now we look at our moles of the hydrogen ions divided by liters of solution. So we're going to get our amount of hydrogen ion after our reaction. That's going to go on top. And then our new amount of the solution after combining the two is going to go on the bottom. And so we divide and we end up with 1.0 times 10 to the negative 3. To find the pH of that, we take the negative log, and our pH is 3.00. So right before the equivalence point, our pH is 3.00. Now we need to do the same thing for part B here, where we have added 51 milliliters. So we're going to essentially have the same setup. Okay, we're going to have the same equation, water, not having any bearing on that. Our beginning hydrogen ion concentration was 5.0 times 10 to the negative 3. Now this time, since we're adding 51 milliliters, our hydroxide concentration is going to be 5.1 times 10 to the negative 3, because we have more hydroxide than we do hydrogen ions at this point in time. So what becomes our limiting reactant? This time, it's the hydrogen. So our change to determine our limiting reactant, we're going to subtract out the amount of hydrogen ions this time. And that's going to leave us with 0 leftover hydrogen ions and 0.10 times 10 to the negative 3 hydroxide ions. Because now, remember, we're just on the basic side of the equivalence point. We've reached equivalent, and now we're on the back side of our titration curve. We've added 51 milliliters now, so we add that to our original 50. We're at 101 milliliters, which is 0.101 liters. And we do our same equation here. Moles of hydroxide ions divided by our total liters of solution. So we're going to have the hydroxide ion concentration of 1.0 times 10 to the negative 3. We take the negative log of that to determine our pOH, which is 3, but we're not looking for pOH, we're looking for pH, so we subtract that from 14, and we end up with a pH of 11. So our pH, then with the addition of 49 milliliters is 3, the addition of 51 milliliters takes us to 11. So the pH increased from 1 to 3 with the addition of the 49 milliliters of sodium hydroxide. But then just adding 2 more milliliters of the base solution caused us to jump from 3 to 11 at the equivalence point. And this is a demonstration of what happens when we have a strong base and a strong acid. This is the characteristic of those types of titrations where we're at 3 and then we're at 11. And, you know, we saw this in the lab last week when you were adding and adding and adding, and then all of a sudden you got that jump. So when you are looking at these types of reactions, just pay attention. Are we dealing with a strong acid, strong base? Is it a weak acid, strong base? You know, pay attention and make sure that you understand what your solutions are when you're doing these types of problems. So now we're going to jump to exercise 17.8, where we have 45 milliliters of a 0.100 molar sodium hydroxide solution added to 50 milliliters of a 1.00 molar acetic acid solution. So you know that sodium hydroxide is a strong base. Well, what is acetic acid? Is it a strong acid or a weak acid? We know it to be a weak acid. So this is going to be a little bit different type of calculation, we're going to work the problem kind of the same, but it's going to be a completely different response, completely different answer, because we're dealing with a weak acid and a strong base. So the first thing we have to do, of course, is get our stoichiometry. So if we have 50 milliliters of the solution, then we have 5.00 times 10 to the negative 3 moles of acetic acid, and we're going to add 45 milliliters of the sodium hydroxide solution to that. So we'll have 4.50 times 10 to the negative 3 moles of the sodium hydroxide. So looking at our equation and then filling in, again, kind of our modified ice table here. We don't consider water. We don't have to worry about it because it's a liquid form. So we start out by plugging in the numbers we just calculated. So we have 5.00 times 10 to the negative 3 moles of acetic acid. And we have, copy that, 4.50 times 10 to the negative 3 moles of hydroxide ions. And to begin with, we have no acetate ions. We see that hydroxide is going to be our limiting reactant here, so we're just going to subtract that. And then we add it over here on this side because this is our product side. So we're left with 0.50 times 10 to the negative 3 moles of acetic acid, 0 moles of the hydroxide ion, and 4.50 times 10 to the third, 10 to the negative third acetate ions. We've changed our volume of our solution. We started out with 50 mils, we added 45 mils, so now we have 95 milliliters or 0.0950 liters. So we need to figure out, okay, so what is then our concentration of the acetic acid here? So we've got to figure out the molarity of these. So we take the amount from our table right here, and we divide it by our total amount of solution here, and we end up with 0.0053 for our molarity of acetic acid. We're going to do the same thing for the acetate ion. We have 4.50 times 10 to the negative 3 moles and a total volume of 0.90950 liters. And so we end up with our molarity of 0.0474. So now we have our molarities, but we're not finished yet. We've got to get to pH. Now, in order to get to pH here, we're going to have to set up our equilibrium expression, or our equilibrium constant expression. Ka is 1.8 times 10 to the negative 5, and we set up the, now this is for our equilibrium expression, where we have acetic acid on the reactant side and the hydrogen ion and the acetate ion on the product side. Well, we need to figure out what is the hydrogen ion concentration. In order for us to determine pH, we need the hydrogen ion concentration. So we're going to rearrange our equation to solve for that. So when we do that, we're going to end up multiplying our Ka times the ratio of our acetic acid and acetate molarities, and we end up with a hydrogen ion concentration of 2.0 times 10 to the negative 6. Take the negative log of that. Our pH is 5.70. We could have also used the Henderson-Hasselbalch equation here for the last step. Using our equilibrium expression and the Henderson-Hasselbalch equation are interchangeable either way here. Okay, so the pH, when we put 45 milliliters of sodium hydroxide in 50 milliliters of acetic acid, is 5.70. So we see a much bigger jump here because we're dealing with a strong base, so it's flipping the equilibrium, trying to, it's pulling it more to the alkaline or to the basic side, and so we go up a little higher than we did like we saw with the last one, where we only jumped to a pH of 3 with the addition of 49 milliliters. Here we jumped up to a pH of 5.70 with just 45 milliliters. The next problem that we get into is looking at calculating the pH at the equivalence point in the titration of 50 milliliters of 1 molar acetic acid, or 0.1 molar acetic acid with 0.1 molar sodium hydroxide. So this time we need to know what is the pH at the equivalence point. We're still dealing with a weak acid and strong base. When we neutralize a weak acid, it produces the anion, which is the conjugate base that's going to react with water. So the pH at the equivalence point is going to be greater than 7. So we have a weak acid, strong base. We should expect the pH at the equivalence point to be stronger than 7, or to be greater than 7. The initial number of moles of acetic acid is going to be the number of moles of acetate ion at the equivalence point. So we can use the volume of the solution at the equivalence point to then calculate the concentration of the acetate ion. It's a weak base, so then we can use Kb and the acetate concentration to determine our pH. So first things first, we have to get our number of moles. So we take our molarity, which is 0.100 moles per liter, and we have 50 milliliters of that. So we have 5.00 times 10 to the negative 3 moles of acetic acid. So that's the first step. Having 5.00 times 10 to the negative 3 moles of acetic acid means that that same amount of acetate ions will form. So we're going to have 5.00 times 10 to the negative 3 moles of acetate ions. Now, looking at the titration curve for a weak acid and strong base, which is on page 741 in your book, it's also in your notes, we can see that the equivalence point for acetic acid and sodium hydroxide is at 50 milliliters. What that tells us is it's going to take 50 milliliters of the sodium hydroxide to reach that equivalence point. So we can, that's not something we have to guess. We can look, at that titration curve and determine how much sodium hydroxide we're going to need. So the volume then of the solution at the equivalence point is the sum of the acid and the base, which in this case is going to be 100 milliliters. So to figure out the concentration of the acetate ion, we can take the 5.00 times 10 to the negative 3 moles that we calculated of acetic acid and divide that by the total volume. That gives us 0.05 molarity for the acetate ions. Now, like I mentioned, the acetate ion is a weak base. And when it is within water, it's going to form acetic acid, but also some hydroxide ions. And we know hydroxide represents a base. So we can calculate the Kb for our acetate ion from the Ka value of the conjugate acid using our water constant. So Kb is equal to Kw divided by Ka, and that equals 5.6 times 10 to the negative 10. So setting up our Kb equation, notice water not a part of that, then we have, I didn't set up an ice table here, but we know that our acetic acid concentration here in this expression and the hydroxide ion are going to be represented by X, and then the acetate ion by 0.05 minus X, we set that equal to 5.6 times 10 to the negative 10. Now, we use our assumption because our Kb is so tiny, then we can assume that X here, 5.05 minus X is equivalent to 0.05. So then solving for X, we end up with 5.3 times 10 to the negative 6, which gives us a pOH of 5.28. Subtract that from 14. Our pH is 8.72. So in this example with a weak acid strong base, the pH at equivalence is not 7. It's going to be on the basic side because the strong base producing, completely dissociating, having those hydroxide ions, that's going to give us a basic pH or an alkaline pH of 8.72. Moving along now to 17.10, moving past titrations, getting now to equilibria of solutions and looking at solubility. So we're introducing a new constant here called KSP, which is our solubility product constant. And what we're looking at here is write the expression for the solubility product constant for CaF2 and then look up the corresponding KSP value in Appendix D. So just like with our Ka and Kb values, we can go to Appendix D to get our KSP values. So what we have to do to write the solubility constant for calcium fluoride is first get our expression. So when calcium fluoride dissociates, it's going to dissociate into its component ions, which would be the Ca2 plus ion and the F minus ion. But we can see from our subscripts that we have 2 fluoride ions. Now this is going to come into play when we write the KSP expression. So to get the KSP expression, we're going to have Ca2 plus concentration times the fluoride ion concentration raised to the second power. So coefficients are going to come into play here. Because we have 2 fluoride ions, then we end up with an exponent 2 on our fluoride ion concentration in the KSP expression. When I go to Appendix D and look that up, that's equal to 3.9 times 10 to the negative 11. So that is our solubility product constant for CaF2. So what does the solubility product constant tell us? Well, it's basically looking at how soluble is this substance in water. So how soluble is it in water? Now we can also use these expressions and look at calculating our KSP from what we observe in the solubility. So the solubility of a substance, as we know, changes. It can depend on the pH, like we looked at in the last chapter. It is affected by concentrations of the other ions in solution that, like, we kind of saw that earlier with the common ion effect. So solubility can change, but the solubility product constant does not. It has one value at any given temperature. So just like the other things we've been looking at, these are dependent upon temperature, and we assume that we're dealing with temperature at 25 degrees Celsius for this. So KSP is a constant. So while solubility can change, the solubility product constant does not. So we have this problem where we are told that solid silver chromate is added to pure water, and some of the solid there remains undissolved. And we have it stirring for several days to ensure that the equilibrium is reached between what is left undissolved and the solution. So when we analyze the solution, we see that the silver ion concentration is 1.3 times 10 to the negative 4. We're going to assume that this silver chromate solution is saturated and there's no other important equilibria at play, and we need to calculate KSP. So basically, we're given the equilibrium concentration of the silver ion in a saturated solution, and we're going to go from there to our KSP. So the first thing we have to do is get our equilibrium expression or equilibrium equation. So silver chromate is going to dissociate into silver ions and chromate ions. And we can see, so the chromate ion is CrO4 with a 2 minus power. That means that we're going to have 2 silver ions for every 1 chromate ion. So when we set up our expression, we can see that we have to square, okay, or raise to the power of 2, our silver ion concentration. Okay, so that's our expression that we're going to have for determining the KSP. All right, so that's step 1. To calculate KSP, we need the equilibrium concentrations of both the silver and the chromate ions. Okay. Now, from the problem, they told us that our silver ion concentration is 1.3 times 10 to the negative 4. All of the silver ions and the chromate ions in the solution came from the silver chromate that dissolved. They told us that there was no other important equilibria there. So we can use the silver ion concentration to then figure out our chromate ion concentration. So here's how we do that. So we know that silver ion concentration is 1.3 times 10 to the negative 4 molar. That means mole per 1 liter. So we're going to plug that in first. So here is our silver ion concentration. And then looking at our chemical equation right here, we know that for every 1 mole of chromate ions, we have 2 moles of silver ions. So our moles of silver we see here cancel out, and we're left with moles of chromate divided by liter, which is molar. So based on our equation, and based on the fact that we have 1.3 times 10 to the negative 4 moles per liter of silver ions, and that we have 2 silver ions for every 1 chromate ion, our chromate ion concentration is 6.5 times 10 to the negative 5 molar. Well, we have silver. It was given to us in the problem. We've just calculated chromate concentration. So now we can determine KSP by plugging in these numbers. So 1.3 times 10 to the negative 4 squared, and we multiply that by 6.5 times 10 to the negative 5. So our KSP for silver chromate is 1.1 times 10 to the negative 12. Of course, this is a very small value, and we expect this for a salt that is slightly soluble. And when we look up in Appendix D to check our answer, we see in Appendix D it is 1.2 times 10 to the negative 12. So we've got something that's very close to that. So we consider that a correct answer. So that was calculating KSP from solubility. So let's look at exercise 17.12, where we're going to calculate our solubility from KSP. So as we saw, the KSP for CaF2 is 3.9 times 10 to the negative 11. Assuming that equilibrium is calculated or is established between solid and dissolved calcium fluoride, and we have no other equilibria affecting solubility, calculate the solubility in grams per liter. So solubility is the quantity that can dissolve in the solvent. And so that's what we're asked to determine here. In order to go from KSP to solubility, we can refer to figure 17.16, which is on page 749 in your textbook. I did not include this one on your notes, but we'll go from KSP to the molar concentration of ions, to the molar solubility, and finally to the mass solubility, which is what they've asked, grams per liter. So that's what we're going to do. So first of all, we come back to our equation for the dissolution, and we set up our ice table to determine our initial and equilibrium concentrations. Then we'll use our equilibrium constant expression and solve, and then use KSP to solve for the solubility. So first things first, we need to fill in our ice table here. I wrote CaF2 in here, but it's a solid, and as we know, it's not going to matter, so we don't really have to worry about it. All we're concerned about is the calcium ion and the fluoride ion here. So what is our initial concentration? Well, it's 0 at first. Okay, we know it's going to change by X, and with fluoride, because we have 2, then it's going to change by 2X. So like I mentioned before, these coefficients are going to be very important. We do have to consider them in looking at the change that's going to occur in our equilibrium expression here. So then we have X for the calcium ion and 2X for the chloride ion. So let's look at our expression for KSP. So here's KSP. We're in that 1:2 ratio, 1 calcium ion for every 2 fluoride ions. So when we plug in our X and 2X, what we end up with is 4X cubed, because we have 2X squared, which will give us 4X squared, times X is 4X cubed. When we solve, or we set that equal to 3.9 times 10 to the negative 11, because we've already looked up our KSP for the calcium ions and the fluoride ions. Now we need to solve. So we divide by 4, and then we take the cube root of that. Okay. So when you're putting this in your calculator, make sure that you don't just do square root, that you actually have to do the cube root on this. And of course, every calculator is a little different, but you should be able to put in the cube root on your calculator. So when we do the math, we end up with X equaling 2.1 times 10 to the negative 4. So that gives us our, equilibrium concentration. So if we were to just kind of plug this in up here, fluoride 2.1 times 10 to the negative 4. But for fluoride, we've got to multiply that by 2, because we have 2 fluoride ions for every 1 calcium ion. So if and I did not do this math earlier, so let me do this right quick. That gives us 4.2 times 10 to the negative 4. I thought that's what it was, but I wanted to double check my math there. So now we have our equilibrium concentrations, our molarity here. Now we're not done yet. Okay. We have to figure out how much then is going to be needed in grams per liter to determine this. So the molar solubility of CaF2 is 2.1 times 10 to the negative 4. And when we look at molar mass, so we've got to plug in molar mass here, 78.1 grams of calcium fluoride in 1 mole, then we end up needing 1.6 times 10 to the negative 2 grams of calcium fluoride per liter of solution. So what does this number tell us? Tell us. Well, it tells us that we can add 1.6 times 10 to the negative 2 grams, which would be 0.016 grams of calcium fluoride to 1 liter of solution. That is its solubility. That's how much will dissolve in 1 liter of solution to create a saturated solution. So not very much. Solubility of this we knew was pretty low. I mean, looking at the value of KSP, we knew the solubility was pretty low. Well, how low is it? We can dissolve 0.016 grams of it in 1 liter of solution. Okay, continuing right along. Exercise 17.13, we start to take a look at some of those effects on solubility. And this first one that we're going to look at here is the effect of a common ion on solubility. So we want to calculate the molar solubility of calcium fluoride in a solution that is 0.01 molar calcium nitrate and 0.01 molar sodium fluoride. So now we're not just putting it in water, we've got solutions that have common ions. In A here, the common ion would be the calcium, and then in part B, the common ion is going to be the fluoride. Our nitrate and our sodium are going to be the spectator ions. Because the slightly soluble compound that we're dealing with here is calcium fluoride, we'll use KSP, which we know from our previous few problems is 3.9 times 10 to the negative 11. The value of KSP, remember, it's a constant and it's only about temperature. So it doesn't matter that we have these other solutes in there. KSP is still going to be the same. But because of the common ion effect, the solubility is going to decrease. So we're going to use our standard ice table here to set up our changes so that we can actually determine how much calcium fluoride will dissolve. So going back to our same equation here, then we're going to get our ice table and figure out our concentration. So again, CaF2, calcium fluoride, is a solid, so we don't have to worry about it. We're just going to look at the calcium and the fluoride here. They tell us that for part A here, the solution is 0.010 molar calcium nitrate. So we already have 0.010 moles of the calcium ions already. Okay. And then our fluoride, we don't have any of it yet. It's just 0. We know that they're going to change by X and then the fluoride by 2X, since we have 2 fluoride ions for every 1 calcium ion. So our expression here There we go. There is our equilibrium concentration. So let's substitute this into our KSP formula, where we have calcium ion concentration times the fluoride ion concentration raised to the second power. And when we solve for X, we end up with 3.1 times 10 to the negative 5 molar. Of course, that's a tiny value for X, and it validates our simplifying assumption that we made, because KSP is such a small number, we, get rid of that X right there so that we only have to deal with 0.010 and we don't have to do the quadratic equation. So that helps us out a little bit there. So now we have that 3.1 times 10 to the negative 5 moles of solid calcium fluoride dissolves per liter of 0.010 molar calcium nitrate solution. Now, if they had asked us for grams per liter, like they did in the last question, we would continue on and plug that in like this. Okay, but they asked us for the molar solubility, so we didn't have to go all the way to grams, but we can see here, just as a comparison, when we're talking about pure water, we can dissolve 2.1 times 10 to the negative 4. But when we put it in that calcium nitrate solution, even less is going to dissolve, okay, because of that common ion effect. Those calcium ions that are already in there are going to interfere. Okay, so looking at part B, the common ion this time is going to be the fluoride ion. So our equilibrium is going to be a little bit different. So your book did not put in a separate ice table in here. So let me just kind of reuse the one that I already have up here. So let me kind of subtract this out here. So this time our initial concentration of the calcium is 0 and our common ion is fluoride, so it's going to be 0.010. We know that's going to change by X and this one by 2X. So we have X and 0.010 plus 2X. So when we come down here, there's where that came from. Calcium ion concentration X, fluoride ion concentration 0.010 plus 2X. And we'll plug in our solubility, our KSP, 3.9 times 10 to the negative 11. X times 0.010 plus 2X squared. So this time we're going to do something a little bit different, as you can see. Assuming that 2X is much smaller than the 0.010, then we're going to get rid of the 2X. So we're just going to square the 0.010 this time. So just like we did up here, and getting rid of the X, okay, we do the same thing here, even though it's 2X. We're still going to get rid of it, okay? But don't forget, we do still have to square it. So we run through the math here, and we end up with X being 3.9 times 10 to the negative 7. So in this example, 3.9 times 10 to the negative 7 moles of solid calcium fluoride should dissolve in our sodium fluoride solution. So even less with this one. So this proves that the common ion is going to decrease the solubility of these solutions. That's what we just showed here. Okay, almost done. Our last couple of things here that we're going to look at is being able to predict the effect of acid on solubility. So the solubility of slightly soluble salts containing basic anions will increase as hydrogen ion concentration increases or as the pH is lowered. So that's what we're trying to figure out here is when looking at these slightly soluble salts, we want to know, are they more soluble in an acidic solution? So in other words, do they contain a basic anion? Well, if we look at the first one, NiOH2, well, yes, we know hydroxide is a basic anion. So the nickel hydroxide there is going to be more soluble in an acidic solution. So yes, this first one is. It produces a basic anion in the hydroxide. So by putting it into an acidic solution, the hydrogen ion then will react with the hydroxide ion to form water. So yes, that one is more soluble in an acidic solution. All right. Looking at calcium carbonate there, when it dissolves in an acidic solution, the carbonate ion is a basic ion. So it's going to dissociate into calcium and carbonate. The carbonate anion is a weak base. So yes, this will be more soluble in an acidic solution. Looking at the barium fluoride solution, we know that the fluoride ion can be a conjugate base of a weak acid. Therefore, our anion is basic. We will have more solubility or an increase in solubility in the acidic solution. The last one, the silver chloride, it is unaffected by changes in pH. You say, well, wait a minute, the chloride ion is also a conjugate base, and it is, but it's the conjugate base of a strong acid, hydrochloric acid. So it has negligible basicity. So this one is not going to be more soluble in an acidic solution than in a basic solution. So the key thing to take away here is look at your anion. Is it a base or is it a conjugate base of a weak acid? If so, then the substances are going to be more soluble in an acidic solution. If your anion is the conjugate base of a strong acid, then no, it's not going to have an effect. And then sample exercise 17.16. In this one, we are looking at precipitation and separation of ions. So in 17.16, does a precipitate form when 0.10 liters of 8.0 times 10 to the negative 3 molar lead 2 nitrate is added to 0.40 liters of 5.0 times 10 to the negative 3 molar sodium sulfate? So what are we looking at? Well, when we combine these two salt solutions, will a precipitate form? So what we've got to do is determine the concentration of ions just after they are mixed and then compare the value of Q with KSP. So when we combine lead 2 nitrate and sodium sulfate, will we get a precipitate? So let's look at this. So first thing we need to do is figure out how many moles of lead 2 are in 0.10 liters of the lead nitrate. So that's what we're looking at here, because we're saying when 0.10 liters of 8.0 times 10 to the negative 3 molar lead nitrate. Well, we need to figure out how many moles of lead do we have. Well, we're going to take our amount, multiply that by our molarity, and here's how many moles we have. Okay. So that's how many moles of lead ions we have. And we're going to take that and divide by the total amount of solution. So we've added 0.10 liters to 0.4 liters for a total of half a liter. So the molarity of the lead ions is 1.6 times 10 to the negative 3. So that's our concentration of lead in our mixture. All right. Now we need to look at the SO4, because if a precipitate forms, if we look back at our equation here, we know that all nitrate solutions are soluble. So if a precipitate is going to form, it's going to involve the lead and the sulfate. Okay, so that's why we're focusing on lead and sulfate, in case you were trying to figure that out. You can use your solubility rules on the back of your periodic table and know that all nitrates are soluble. So will a precipitate form from lead sulfate? So we've gotten our concentration of lead. Now we're going to do the same thing for the sulfate. We have 0.40 liters of sodium sulfate. The concentration of that is 5.0 times 10 to the negative 3. That gives us 2.0 times 10 to the negative 3 moles of sulfate ions. And we divide that by our total mixture volume. So that gives us 4.0 times 10 to the negative 3 for our concentration of sulfate ions. So let's figure out Q. To figure out Q, we multiply our concentrations together, and we get 6.4 times 10 to the negative 6. And if we look at the KSP value for lead sulfate, which is 6.3 times 10 to the negative 7, which we found from Appendix D, Q is greater than KSP, then we will have a precipitate form. So your rules for precipitation are in your notes. They're also at the bottom of page 759. If Q is equal to KSP, the system is at equilibrium. If Q is less than KSP, we will not get a precipitate. If Q is greater than KSP, then we will get a precipitate. So the important thing to remember about these types of problems when you first get started, figure out what your precipitate will be. And then from there, figure out your molar concentrations of the ions involved. In this case, the lead 2+ ion and the sulfate ion. Set up your solubility expression, your KSP expression. In this case, notice that we didn't have any, exponents here or here. Why? Because a 2+ and a 2- are going to form a neutral substance, a neutral compound. So you have to think about, when I put these together, what will the overall compound be? And that will help you determine if you're going to need any exponents here and here. So for example, if we had, let's say, sodium here, just as an example, then we would end up with 2 sodiums for every 1 sulfate so that we could get a neutral compound. So then when we would write that expression, we would have to square the sodium because it's Na2. All right, so just keep that in mind. Think about what your compound is going to be when you combine your 2 ions to determine what exponents you might need in your expression. So again, we set this up just like a KSP expression, multiply, and we get 6.4 times 10 to the negative 6. We compare that to the actual KSP. It's less, it's greater than KSP, so the lead sulfate will precipitate. Our last problem that we're going to look at in chapter 17 tells us that we have a solution that contains some silver ions and some lead ions, and we're going to add chloride ions to that. And when we do that, both AgCl and PbCl2 can precipitate. And we need to know what concentration of chloride ions will begin the process and which one precipitates first. All right. So we've got some sodium ions, some lead-2 ions in a solution, and we add chloride ions, and we want to know what concentration is needed to force precipitation to happen, and of the 2, which is going to precipitate first. So we set up our KSP expression for the first one. So we're going to start with silver and silver chloride. It's a 1-to-1 ratio there. And the KSP for this is 1.8 times 10 to the negative 10. Again, we can go to, or they give us these in the problem, but we can always go to Appendix D to figure that out. So what we have to do then is solve for chloride ions. We've got to determine how much, what is the concentration of the chloride ions that's going to cause this precipitation. So we take our silver concentration that they told us in the problem, okay, the 1.2 times 10 to the negative 2. We're going to multiply that by our chloride ion concentration and set that equal to our KSP. So then we need to solve for chloride ions, and when we do that, what we find is that we need 1.8 times 10 to the negative 8 moles per liter of chloride ions to cause a precipitate to occur here. So any chloride in excess of this amount is going to cause silver chloride to precipitate. All right. So now we need to do the exact same thing for the lead-2 chloride. So we set that expression up equal to KSP. Notice we have an exponent here because it takes 2 chloride ions for every 1 lead 2+ ion. We're going to solve for chloride. So we take our lead, 2.0 times 10 to the negative 2, that came from the problem right here, plug it in. And this time, when we solve for Cl2, or the Cl, it's raised to the second power, we have to take the square root. So we need 2.9 times 10 to the negative 2 moles per liter to make the lead-2 chloride precipitate out. So we have to have an excess of that. So now we're going to compare the chloride ion concentration. So we've determined how much chloride it would take to cause precipitation. But the question also said which one precipitates first. So we have to look at and compare the two chloride concentrations there. AgCl is going to precipitate first because it requires much less chloride, 1.8 times 10 to the negative 8 moles per liter, compared to 2.9 times 10 to the negative 2 moles per liter. So, yes, we can cause precipitation by adding this much chloride. We'll get AgCl. Adding this much chloride, we get PbCl2. AgCl is going to precipitate first because it takes much less chloride to cause that to happen. So we could put just this amount, 1.8 times 10 to the negative 8, and get silver chloride. If we don't add any more than that, then we won't ever see the lead 2 chloride precipitate out. I hope that this has helped you with titration and solubility problems. As always, if you have questions, please feel